Alright, it's time to talk about the so-called hurricane cookbook. Let me tell you about this word cookbook a little bit. This is a word that comes from like teaching and pedagogy and so on, where you're talking about how do you explain to students the list of things you got to have to make something. I mean, if I was making a lasagna, I know I need noodles and sauce and cheese and herbs and stuff like that. And if I don't have noodles, I don't know what I'm making, but it isn't lasagna. And if I don't have cheese, I don't know what I'm making there, but it's not lasagna. In the same sort of, in order to be a lasagna, it's got to have all those things, okay? In the same sort of way, this is a teaching technique where we talk about the things you got to have to make a hurricane, okay? It's the hurricane cookbook. We stick with that terminology with hurricanes just because the original scientific research that figured all this stuff out, that was the terminology they tended to use too. Alright, so let's talk about the things you need. It turns out there's 6 main ingredients on the hurricane cookbook. And the first one is you need to have high sea surface temperatures. SST is an abbreviation for sea surface temperatures. The surface of the ocean over which the hurricane is forming has to be pretty darn high. I said here 26 degrees Celsius. That's right around 80 degrees Fahrenheit. And that's almost like bath water. That's unpleasantly warm water to be like swimming in or something like that. Why do you need to have such high water temperatures in order to get a hurricane? Well, it's all about that story, the fundamental problem that a hurricane is having again. Hurricanes need tons of evaporation off the surface, and big strong winds are part of the story, but another part of the story is warm water evaporates faster than cold water does. It's a little hard to tell it when you're talking about like, here's a cup of warm water on the counter and here's a cup of cold water, but that's because you don't have a 100-mile-an-hour wind blowing across the 2 cups. All right? It's actually pretty significant how much more evaporation happens over warm water than over cold water. The great scientific jargon for that is we say that there is a greater flux of sensible and latent heat. Okay, sensible heat flux is like the conduction of heat out of the ocean, and latent heat flux is about the evaporation rate off the ocean. Both of those are much better for the hurricane if the water's warmer. That being said, hurricanes are so dumb. If they're moving, let's say, from east to west towards Central America, and there's an area of warm water over here and an area of cold water over here, the hurricane, even though it would be stronger and a bigger, longer-lasting storm if it went over here by the warm water, it doesn't do that. Hurricanes don't in any way seek out warm water or anything like that. They're just being pushed along by the winds. Now let's combine that with our second idea about something in the hurricane cookbook, and that's going to be the Coriolis Force. Hurricanes need the Coriolis Force, but kind of in a complicated way. Back in, what was that, Module 2 or something in the class, we learned all about how the Coriolis Force was part of the story of the geostrophic wind, where the Coriolis Force was balancing the pressure gradient force and so on. Well, that works in certain things like mid-latitude cyclones, but that's not how hurricanes work. But the force balance that hurricanes do have does include the Coriolis Force. Okay? It's just a much more complicated, we don't want to get in the business of drawing arrows to talk about different forces around a hurricane. It gets way too complicated way too fast. But Coriolis Force is part of the story. So you're going to have the Coriolis Force, and remember, the Coriolis Force is 0 at the equator. In fact, it's pretty darn close to 0, even close to the equator. You got to be at least 5 degrees off the equator before there's enough Coriolis Force to work with to create the circulation around a hurricane. And realistically, 10 degrees off the equator, 15 degrees off the equator, it's going to be better and better for the formation of hurricanes. Hurricanes are not in geostrophic balance, but they are in a balance that does require the Coriolis Force. We're just not going to retread that. We're not going to go back and reinvent that wheel. This tells us something important about hurricanes. Hurricanes can't form at the equator, and they can't cross the equator, because either way they'd have to hit a point where they have no Coriolis Force and they just wouldn't work. And in fact, if we go back to that diagram we had that sort of gave us an explication of the where hurricanes tend to be, we see that, well, actually, yeah, they're kind of all in pretty tropical places. I'm not terribly surprised to find out that those places have warm water. They're off the coast of Central America, or off the coast of India, or off the coast of Northern Australia, and so on. Even though there's undoubtedly quite warm water along the equator, we don't get hurricanes there. So this plot is starting to make a little more sense as to what was going on. Now there's 4 more ingredients yet, though, in the hurricane cookbook, and one of them is about instability. Hurricanes need an environment that's fairly unstable, where air parcels can rise and lower, for that matter, because you're going to lower them in the eye, pretty easily. Remember, instability is about how much the atmosphere is resisting vertical motion. And the truth of the matter is, Our hurricanes can't put up with that crap. They are going to need, an individual hurricane will have several hundred thunderstorm cells in there. We need rising motion in the eye wall and in the rain bands. We need sinking motion in the eye. We can't be having the atmosphere resist all that vertical motion. So in general, we're going to have parts of the tropical atmosphere where it is relatively unstable. Now, as it happens, that rules out an important place, the subtropical highs. The subtropical highs, which remember sit at about 30 degrees north and 30 degrees south, are regions of sinking motion, and that sinking motion produces stable conditions. You actually had a homework question, if I recall correctly, where you even had to kind of work through why sinking motion causes stable conditions. But again, we're not going to reinvent the wheel on that kind of stuff. Sinking motion produces stable conditions, like temperature inversions and so on, and hurricanes can't deal with that. They cannot be fighting the stability of the atmosphere. So if you take a look at this plot again, and I just sort of throw on there some H's to show where typical locations of the subtropical highs are, you see that those are not places in general where we see a lot of hurricanes. Because in general, that's just not a favorable place for the hurricanes to develop. It's too stable. Alright, our fourth ingredient on the hurricane cookbook, wind shear. Oh, let me be more clear. No wind shear. Wind shear, remember, is about how winds change with respect to height. So if like the winds are from the east at the surface and the winds are aloft or from the west, you have wind shear. If throughout the whole depth of the troposphere, the winds are all going the same direction and the same speed, you don't have wind shear. Now, I'm not talking about when I say no wind shear, I don't mean like in the hurricane itself. The hurricane itself has all kinds of crazy wind shear going on as the bottom of the hurricane rotates one way and the top rotates the other. I mean in the environment around the hurricane. Hurricanes hate wind shear, and that tends to be the reason why a hurricane doesn't form when everything else is right, is there's too much wind shear. It's hard to explain exactly why hurricanes hate wind shear so much, but let me give you part of the story. Keep in mind, hurricanes have a lot of structure. They have rain bands and an eye wall and an eye, and the slope of the updrafts in the eye wall is related to how strong the hurricane is and so on. And all of that is just made of air. It's relatively easy to mess that up if, like, winds are pushing the bottom of the hurricane one way and the top of the hurricane the other way. It's relatively easy to mess up the structure of a hurricane with wind shear. Now, it's actually somewhat more complicated about that than it's also part of the story of how it redistributes the latent heat release in the storm, but that is, I think your book tries to say a little bit about that. But in general, it's just really hard to maintain that elaborate structure that hurricanes have if you're in an environment with wind shear. And the main culprit here is going to be jet streams. Because if hurricanes are in the fairly tropical places where there's winds from the east at the surface, if you've got a jet stream, like the subtropical jet stream or something like that, coming from west to east above there, that's a whole lot of wind shear. Hurricanes hate that. So as a consequence, hurricanes don't cross the jet stream, they don't form under the jet stream, or anything like that. They can't deal with that. That also, by the way, is part of the story why hurricanes don't in general cross fronts. If you've got a cold front or a warm front out in the ocean, over the ocean someplace, the hurricane generally can't cross that either. Not because there's something magical about a cold front or something like that. Well, I guess it is kind of magical. Remember the thermal wind relationship? If you've got a cold front at the surface, you've got a jet stream above it. It isn't actually the cold front that the hurricane cares about. The hurricane cares about the wind shear associated with that jet stream. The fifth answer about the Hurricane Cookbook is a little bit complicated. This is the story that we need high relative humidities throughout the middle of the troposphere. You want, not necessarily, it'd be lovely if you had high relative humidity at the surface too, but the mid-troposphere becomes kind of important. This is about entrainment again. Remember entrainment? This idea that air from outside of the thunderstorm's updrafts tries to get into the updrafts or ends up mixing into the updrafts? Well, if that air that you bring in from the outside of the updraft and you entrain it into the updraft, if that air is dry, it's going to be making my updraft weaker, right? I mean, we're going to be evaporating raindrops, which is a cooling process and so on. If I'm going to make a hurricane, I need hundreds of healthy thunderstorms. I can't be putting up with that crap. I can't be having the individual cumulonimbus clouds being destroyed by dry air entraining in from the outside. This turns out to be a major limitation as to where hurricanes can form in the Atlantic, because we have a big source of dry air just off to our east, namely the Sahara Desert. The Sahara Desert produces very hot, dry air masses that then the trade winds push out over the Atlantic, and hurricanes hate that. Even if down near the surface the air has become moist by contact with the ocean and evaporation and so on, if you try to have an updraft into that Saharan air mass, any air that you entrain into your updraft is going to just be astonishingly dry. It's going to evaporate all your raindrops, you're going to have all that cooling do all that evaporation, none of that's going to work. So that takes a little bite out of the parts of the world where we can expect to find hurricanes as well. Finally, one thing we need to have in order to form a hurricane is an initial disturbance. This has to do with the fact it's easy to misunderstand what hurricanes do. You might think hurricanes start off small, little baby hurricanes, and they grow. That isn't the way it works at all. Hurricanes start off disorganized, a group of thunderstorms that are not all lined up into an eye wall and in rain bands and stuff like that, and then they get organized. So you have to have some thunderstorms to work with first, and then the winds of the nascent or developing hurricane will start organizing them into that structure of the eye wall and into the structures of the rain bands and so on. So you got to have something to work with. Now, as happens in the Atlantic, this is not a problem because we have a great source of initial disturbances off to the east, and that is West Africa again. Not up by the Sahara Desert, but farther to the south along the coast of West Africa where they have a monsoon. Oh my goodness, there's all kinds of clusters of thunderstorms and squall lines and things like that that are part of the West African monsoon that then get carried by the trade winds, off into the Atlantic, and they form lovely initial disturbances that the winds around the developing area of low pressure can start to organize and start producing an eye wall and so on. Oh, the Hurricane Cookbook is a powerful tool to understand where and how hurricanes can happen. Let's answer three quick questions about the Hurricane Cookbook before we go on and talk about damage. Question 4. Why do hurricanes only form over warm water? A. Warm water emits less radiation than cold water does. B. Warm water has less friction than cold water does. C. That's where high enough evaporation rates are possible. Or D. Hurricanes can form over, it's a trick question, hurricanes can form over cold water or warm water, it doesn't matter. Which of those 4 is the right choice? Take a look at those 4 options and get a little feedback before you move on to question 5.